So, good morning everyone. This is Dr. Vinay. Today we will see one of the concepts in power electronics called single phase full bridge converter. This is a basic circuit diagram of single phase full bridge converter. Right. So this is a single phase full bridge converter. First of all, we need to know what is a converter. A converter which converts energy from one form to another form. That is, we have five different types of converters. That is, the converter which converts AC to DC, we can call it as a rectifier. And the converter which converts DC to AC, we can call it as an inverter. And the converter which converts fixed AC to variable AC, we can call it as a AC voltage controller. And the converter which converts fixed DC to variable DC, we can call it as a chopper. And the converter which converts fixed frequency to variable frequency, we can call it as cycloconverter. A converter is a converter which converts a waveform or a voltage of one form to another form. Today's class we will see the full bridge converter. Why we are calling it as a full bridge? We have different types of rectifiers here. That is three single phase rectifiers and three phase rectifiers. In single phase and three phase rectifiers, again we have two different type of classifications. The first one is half wave, and the second one is full wave, and the third one is half bridge, and the fourth one is full bridge. So today we will see the full bridge converter. Why we are calling this one as a full bridge converter? The first thing is why we are calling this one as a full bridge converter. Why? Because here this converter, especially the full bridge converter, will converts the entire input AC waveform of both of cycles into a DC waveform, right? So that's why we are calling it as a single phase full bridge converter. Let us see the structure of the full bridge converter. So we have four thyristors, that is T1, T2, T3, T4, right? And we need to follow the three conditions while operating the full bridge converter. The condition one is no two devices of the same length will conduct at a time, right? That is T1 and T4 does not conduct at a time. Doesn't conduct at a time. Similarly, T3 and T2 doesn't conduct at a time. So this one we can call it as a one leg, and this one we can call it as another leg, right? So that's why we are calling this one as a two bridge converter. Because it looks like a bridge converter. So here T1 and T3 we can call it as a positive group. T1 and T3 we can call it as a positive group. Upper group and then T2 and T4 we can call it as a negative group, and we can call it as a lower group. The first condition is no two devices of the same length doesn't conduct. And the second condition is no two devices of the same group will conduct at a time. That is T1 and T3 does not conduct at a time. Similarly, T2 and T4 does not conduct at a time. So then how can we get and how this converter is going to convert AC to DC? Simply we need to give the firing pulses. How we are going to generate the firing pulses? We have different types of modulation techniques. We have different types of modulation techniques. With the help of modulation techniques, we are giving the pulses to each tyristors given D2, D3 and D4 so that the bridge is going to convert half wave, AC waveform to DC waveform. So let us see the operation of the full bridge converter. So for the positive off cycle, here as soon as we are giving the supply voltage, AC voltage, let us see here, this one is an AC voltage, right? So So this is the maximum voltage Vm, and this is the negative at maximum, and this is the half cycle pi, and this is full cycle pi. So this is an AC waveform having a frequency of f here, and f is inversely proportional to 1 by time period. So we can consider here x-axis as omega t angular time period, and we can on y-axis we can consider a voltage magnitude, right? So for the positive obstacle, whenever the input voltage is getting positive from 0, the current will flows. The current will flows from here phase neutral. The current will flows from phase to T1, and we know that the thyristor is a unidirectional device which only conduct from anode to cathode. So even though the current is flowing to the anode or the T1, it doesn't conduct by because it is a convert device. It will conduct only if we are giving the gate pulse. And the gate pulse we already know we are generating from the formation gate. So whenever we are giving the gate pulse at some delay angle, what is this delay angle? Delay angle we can call it as firing angle, right? This is one we can draw it as a gate pulse waveform. So 0 to 180 degrees, half of one we can call it as a pi wave or 90 degrees. Now, as soon as we are giving the supply, we are not giving the gate pulse to the thyristor, so it doesn't conduct. So whenever we are giving the gate pulse to the thyristor, it will start to conduct. Suppose I am giving the gate pulse at 30 degrees. So now I will get the waveform, I will get the output voltage from the 30 degrees, and it will reach us to maximum, and we will get to 180. Again, so after the thyristor T1 is conducting, the current will start to flow here, and then it will comes to load RL. Again, it will go to T2. So it doesn't goes to T1, so T4. Why? Because we already know we need to follow a condition that no two thyristors in the same line doesn't conduct. So obviously the current will always goes from high potential to low potential. So it will take the path of from phase to neutral through T1, load, and mandatory we need to the gate pulse to the T2. So whenever we are giving the gate pulse to the T2, that is IC2, right? So now I will draw here another gate pulse. So we need to give the same delay angle. So if you are maintaining the same delay angle for both positive off cycle as well as negative off cycle, then we will get the symmetrical output. The symmetrical output in the sense we will get the output waveform of same magnitude. If you are not giving the same gate pulses for the both off cycle, then we will get the asymmetrical pulse. So here for the positive off cycle, we are giving 30 degrees as a delay angle or firing angle. The same 30 degrees we need to maintain for the negative off cycle. So negative off cycle starts at 180. So 180 plus 30, 210. So now we need to give the gate pulse at 210 here. So now as soon as we are giving the gate pulse at 210, now here for the positive off cycle, the thyristor T1 will conduct, and then here T2 will also conduct, and the current will flows back to neutral. So in the positive off cycle, T1 and T2 will conduct. So this gate pulse IG1 and IG2. So both the gate pulses are giving at same period of alpha delay angle of 30 degrees. So whenever we are giving the gate pulse at 30 degrees delay, now T1 will conduct and the current will flows to the load, and then T2 will also conduct and the current will get back to neutral. So that we will get the output voltage of V0 starting from 30 degrees. So here 30 degrees, and it will reach us to maximum 90 degrees, and again it will get 0 at 180. As soon as the supply voltage is getting 0, then as it is a AC waveform, the supply voltage, the magnitude of voltage will get reverse after 180. So now the current will flows, and this will becomes phase, and this will becomes neutral. Now the current will flows in the second leg through thyristor T3. So the current is now shifting from T1 to T3. So now this one, the current will flows to T3. As soon as the current is reaching to T3, it doesn't conduct. We already know that the thyristor is a unidirectional device. So again, it is a control device. We need to give the gate pulse. So now here, after in the negative off cycle, after 180, the same